Okay, welcome to your lesson on reciprocal graphs. The warm-up up at the top of the page here, that is included in a separate video. Since that was my first video ever, I will post that on my website separately. If you would like more practice with sketching one complete cycle of a sine graph, I would highly recommend checking out the video and checking your answers to the example at the top. So today we're talking about what do the reciprocal graphs look like, and the reciprocal functions are that of cosecant, secant, and then finally cotangent. So to analyze what these graphs look like, what we're going to do is take a look at what does one cycle of the sine graph look like, and then think about how I can use that information to figure out the graph of cosecant. So looking at this graph at the bottom of the first page here, you can see that we have that first cycle of sine graph as a dotted curve there. And if you think about taking some of these y values and then flipping the ratio, that would be the resulting ratio for the graph of cosecant. So what winds up happening is if you look at, for example, the point at pi over 2 comma 1, that point winds up staying on the graph of cosecant. And so does the point at 3 pi over 2 comma negative 1. Okay, those points would be in common between both the sine and the cosecant curves, because when you flip the ratio 1 over 1, you wind up getting 1 over 1 again. Now, where the sine graph winds up equaling 0 at 0, pi, and 2 pi, that winds up being places where the cosecant curve is undefined. Imagine taking the ratio 0 over 1 and flipping it, you would get 1 over 0, which is undefined. So what I'd like you to do is on the axes here, go ahead and draw in asymptotes at 0, pi, and 2 pi. Just like what we did with sine and cosine the other day, we're only sketching one cycle for now, but clearly this graph would extend beyond these constraints from 0 to 2 pi. Think within each of these regions here. If I think about the section from 0 to pi, look at some of those values for the sine curve, like where the y value is 1/2 or 1/3 or 1/4. What happens is when you flip those fractions, you get things like 2, 3, and 4. So as the fraction gets closer and closer to 0, the values for cosecant actually wind up getting larger and larger and larger and head off, in fact, towards infinity. So what's going to wind up happening is you get a curve that looks pretty parabolic in that first section here. That's what cosecant looks like from 0 to pi, and then finally in the second section of the graph here, we get a very similar looking curve underneath the x-axis from pi to 2 pi. So this is what one cycle of cosecant looks like from 0 to 2 pi. When I go off to the side here and I list some of these key pieces about the cosecant graph, to be honest, the domain is one of the tougher things to list, but let's see if we can analyze it. The domain includes almost all real numbers, except we certainly have to exclude where we have these asymptotes. So if you look at our example here, we have asymptotes at 0, pi, 2 pi, and if we continue the pattern, we would also have asymptotes at 3 pi and 4 pi, and in fact, in the negative direction, we would also have asymptotes over there as well. So the way we're going to represent all these pi's is we're going to say except pi times n, where n is an element of the integers, which is something we're used to writing, and I think, and I hope that this answer for the domain makes sense, because we're saying, all right, if I do any integer times pi, those are the values we would have to exclude from the domain. Those are the places where we have vertical asymptotes. For the range, basically if you think about the range of sine as being -1 to 1, notice how the range for cosecant is everything outside of that. Okay, we can still include -1 and 1, but basically cosecant is not defined anywhere in between -1 and 1 on the y-axis. So the way we represent the range is from -infinity to -1, bracket, union 1 to infinity. And then finally, as of right now, we've only sketched one cycle of this cosecant graph, so its period is 2 pi, just like the period of sine. And this does wind up having some symmetry here, just like the sine graph would. So if you were to continue this to the left of 0, you would kind of see this matching curve. Oops, that's not what I wanted to do. Something like this, okay? So hopefully you can imagine that if I were to look at this graph and say, what kind of symmetry does it have? It has origin symmetry. All right, so that's basically what the cosecant graph looks like, and at the end of the lesson, we'll also take a look at some quick transformations. We don't get quite as far with transformations as what we do with the sine and cosine graphs, but we can do some pretty basic ones for cosecant. Okay, if we take a look on the next page at what secant looks like, we're going to use a very similar thought process. And if I start with where the cosine curve equals 0, remember before that wherever cosine was 0, that means that in this case secant will have an asymptote. So go ahead and start at pi over 2 and 3 pi over 2, create those vertical asymptotes there. And the places where cosine is at 1, and then at pi when we're at -1, again, flipping those ratios wind up keeping those values the same. So if I think about what happens as I approach, for example, from 0 to pi over 2, since the value of cosine is decreasing there, think of y values like 1/2, 1/3, 1/4, the graph of secant would be increasing. It would go from 2 to 3 to 4 and so on. So you wind up getting a curve that approaches the vertical asymptote from 0 to pi over 2. In between pi over 2 and 3 pi over 2, you get, again, this kind of upside down parabola looking shape in the middle. And then between 3 pi over 2 and 2 pi, again, you're going to approach that vertical asymptote as you get close to 3 pi over 2. And then at 2 pi, the y value there is, in fact, 1. And if you look at the graph of secant, I think a really good way to remember what secant looks like, just as a parent function, is that secant is sad. It kind of looks like a sad, crying face to me. So if that's a good way to remember it, then hopefully that's something you guys can use as a resource here. But secant to me is sad. Okay, let's talk about those same things of domain and range. So in this case, the domain, again, you can write it as all reals except we want to exclude where those vertical asymptotes are. Okay, the asymptote pattern is a little bit different than for cosecant, because notice how we have asymptotes at pi over 2, and then 3 pi over 2, and the next one would occur at, hopefully you're saying right now, 5 pi over 2, and then 7, and then 9, and so on. So what we want to basically do is exclude certain multiples of pi over 2. So you can write it as n times pi over 2. But you do have to specify that n is an element of the odd integers, which again is kind of an odd way of expressing a domain, but that really does cover all of the places where the secant graph has vertical asymptotes. There are other ways mathematically of writing this, however, I think this is probably the easiest notation-wise. As far as the range is concerned, it actually has the same range as cosecant, -infinity to -1, union 1 to infinity. And then finally, we do have a period of 2 pi. And if I were to go to the left at all of the y-axis here, you would see on the negative side that this curve does continue on to the left. That kind of parabola-looking shape would keep going. So this graph here actually winds up having y-axis symmetry, just like the graph of cosine would if you were to extend to the negative side of the x-axis. Okay. So here's a little bit about the parent function secant. And again, if you take a look at the end of the lesson, you'll see some more transformations with secant. Okay, so finally that brings us to tangent and cotangent. We haven't really looked a lot at the graph of tangent because it's not as nice to do some of those transformations like phase shifts and vertical shifts and changes in frequency to the tan curve as it would be to, let's say, the sine and cosine curves. So what you're seeing right now graphed in that dotted form is the graph of tangent. You may remember that it would have vertical asymptotes at pi over 2 and 3 pi over 2 because tan is sine over cos. So how do I know where tan has asymptotes? It's where cosine of x equals 0, which happens to be, if you look above, at pi over 2 and 3 pi over 2. Okay. So then if I were to, again, take this knowledge and say, how do we figure out what the graph of cotangent looks like, where tan equals 0, which is at 0, pi, and 2 pi, the graph of cotangent would be undefined. So we have an asymptote here at 0, at pi, and then at 2 pi. And again, similarly, if we think about actually in this case where the asymptotes are, think of an asymptote as being the ratio 1 over 0, something of that form. If you flip the ratio 1 over 0, you actually get 0 over 1, which means that the graph of cotangent equals 0, where the graph of tangent had asymptotes. So I understand that's probably a little tricky conceptually, but again, to get an asymptote, we think of the ratio as being 1 over 0. When I flip that, you get 0 over 1, so that's why cotangent equals 0 at those values of x. Okay. If you were to take these graphs and flip the ratios around, so again, thinking about where tangent equals things like, 1/2 or 3 or 4 and things like that, and flip those fractions around, the resulting graph of cotangent has a similar type curve to it, but it kind of goes in the opposite direction. So here's what a cycle of cotangent would look like if I graph it from 0 to 2 pi. Okay, and it is a little confusing to look at them on the same set of axes, so eventually it might be beneficial to separate those somewhere to see what does tangent look like versus the graph of cotangent. It's a little tough for me to write on this with my pen here, so I'm going to try my best to fit in these boxes the domain and range for tangent and cotangent here. If you look at the tangent graph and you were to look back at another example, I hope you would find which domain it matches from an example we've graphed so far today. Tangent has asymptotes at pi over 2 and 3 pi over 2 and 5 pi over 2, so it's actually the same domain as the secant graph. So rather than writing that all over again, refer to the example up above. This way you guys can write in that all over again, that it's basically all real numbers except multiples of pi over 2 that are odd. And again, the way that we wrote it at the top of the page here, I think, is the most concise way of writing that domain. Okay, similarly for cotangent, we have asymptotes at 0, pi, and 2 pi, and that should sound familiar from the front where we graphed cosecant. So this is actually the same domain as cosecant. Okay, so we have the domain covered, and again, you can go back and copy what we had on the front for cotangents for the domain there. The range of these functions are actually the same. The range would be actually all real numbers, right? The graph goes down forever, goes up forever, so the range is all reals. And what's interesting about this graph is that typically when we graph things like sine and cosine, their period is 2 pi, but what you should notice for the graph of tan and cotangent is one complete cycle of those graphs are completed by the time you get to pi. So it's a little bit different in terms of the period of these functions here. And finally, the symmetry is that we have origin symmetry for actually both. So tangent and cotangent both have the same type of symmetry here. Okay, so that's a little bit of the basics as far as what do the reciprocal graphs look like. And again, if something went too fast in this part of the lesson, because I realize I am probably going quickly here, certainly replay this video later on. I will post it on the website for you guys to check out. This way you feel confident with the material and we'll be able to graph these curves later on. What I'd like you to do on the last page of today's notes is go ahead and take a look at what are some of the transformations we can do to the graphs of secant and cosecant and even cotangent. Okay, so we have number 4, y equals -3 cosecant x. Just off to the side here, I'm going to remind you that a minute ago, cosecant looks something like this, right? It had asymptotes at 0 and pi and 2 pi. So if that's the graph of one cycle of cosecant, how does the effect of that -3 change what that parent function looks like? Well, if we think back to what we did on Monday this week, which is the basic transformations of sine and cosine, the 3 out front is going to be a vertical stretch. It's kind of a change in the amplitude there. And the negative is going to flip the graph over. So think about stretching the graph that I just drew to the right and then flipping it over the x-axis. So we're going to now have a sort of range that includes everything except what's in between -3 and +3 here. But those asymptotes are going to stay in the same place. So if you want to mark where pi is, and you also want to mark where 2 pi is, you can go ahead and put those asymptotes in the same place. We can even have one at 0 if you want to include that one initially. And in between 0 and pi, what you would see is instead of having the parabola that opens up, it would be that parabolic shape that opens down with a max height there of -3, according to that stretch. And again, I apologize for the accuracy here. Hopefully you guys can understand it's not the easiest to use this at home, but it's working out okay. Okay, in the next section between pi and 2 pi, very similarly, you're going to get to that max. I should say the min value in this section is going to be +3, and you get a curve that looks something like this. So -3 cosecant x, without using a calculator or anything like that, I can base it off of what I saw from the parent function initially to start. If I think about 2 secant of x minus pi over 2, what's going to happen here is actually there's two effects that happen. If you look at what's inside the parentheses, we've talked about the effect of that horizontal translation here. This is going to be a phase shift to the right of pi over 2. Okay, so that would be the first transformation we would see. And finally, the 2 on the outside would be that vertical stretch. So again, think about secant. Remember, secant is sad. Okay, here's a really quick look at what secant looks like again. So if I move everything to the right pi over 2, what in effect happens is that those asymptotes are going to move as well. So the asymptotes were at pi over 2 and 3 pi over 2. Now the asymptotes move to pi and 2 pi, which sounds very familiar to us from a second ago with cosecant. When you translate the graph of secant, pi over 2 to the right, it winds up corresponding with the graph of cosecant. So actually, even though this is a secant curve, because of the phase shift here, it's going to look very much like a cosecant graph. If you were to go ahead and go up 2 and down 2 for that max and min value, you're going to wind up seeing a curve in the first section from 0 to pi that looks like this. And then in between pi and 2 pi, you wind up getting a graph that looks like this. Okay. So again, I hope that based on if we're okay with what the parent functions look like, we can figure out, we're not going to get too crazy with the transformations on cosecant and secant. Uh-oh, where'd I go? Hang on. Okay, we're back. And let's see, at the end here, let's just finish up with number 6. We can talk about number 8 on Thursday if we need to, as far as what happens when you shift cotangent. But finally, for number 6 here, again, think about cosecant, which we graphed just a minute ago here. Okay. What we notice here is that we don't have a phase shift this time, but we do have an increase in the frequency. So if the frequency is now 2, what that means is that the period of this cosecant curve is pi. So I need to see all of this happen that I just drew over here by the time I get to pi, which means you'll see that repeat itself by the time I get to 2 pi, if that's the interval that I'm graphing over, which I don't know if it says that in the directions. It doesn't necessarily say that, but you know what? Let's graph from 0 to 2 pi so you kind of get the idea of what this looks like. Now again, there are two other things that will play an effect here. We have the -4, which would flip it and stretch it. And the other thing that's going to happen is we'll see those 2 cycles by the time I get to 2 pi. To make the graph kind of fit nicely here, I'm going to call this 4 and this -4. So I hope you're okay with that change. Okay. So we'll label this as pi and this is 2 pi. If we think about that first cycle here, again, you're going to have an asymptote actually at pi, but also an asymptote at pi over 2, right? Think about taking what I graphed off to the right there and fitting that by the time you get to pi. The other asymptote then occurs at pi over 2. And again, with the flip that's happening because of the negation of the amplitude here, you wind up getting this in between 0 and pi over 2, and then this in between pi over 2 and pi. So that's what the first section of the graph looks like, and then if we were to continue all the way to 2 pi, you would get those asymptotes to repeat, 3 pi over 2 and 2 pi. And we repeat one more cycle of that same curve there. Okay. So that's pretty much it as far as reciprocal graphing goes. Tomorrow our plan is to go over anything that you have with reciprocal graphs, Certainly you can ask me more questions about the transformations of sine and cosine, and I hope you are all well-behaved students today. I expect an excellent report when I get back tomorrow, and on Thursday we got some inverse trig coming your way. So now for the rest of the period, you guys will be working on that homework worksheets, and I will check in with you tomorrow. Again, anything that you may have missed from class today, if it went too fast, check this out on the website later, and you guys should be good to go. All right, have a good one, guys. We'll see you tomorrow.